Okay, there we are. I haven't written anything, but everyone can see it.
Yep, we see it. Well, we see, yeah.
Okay, good. So, so what I'll talk about today is a classical topic, namely homological dimensions over commutative Noetherian rings, and in particular, how to detect finiteness with vanishing of Ext and Tor. So throughout the talk, R is going to be a commutative Noetherian ring.
We see your screen twice. Is that what you want us to do?
That's what I want, because this is a technique I developed when I was teaching online. I'm going to scroll so that
okay.
Yeah, so that you have at least two things at the same time, because this is one of the things I don't like about slides, is that you have too little history. But when doing it like this, you can have a little bit of history of what's been going on.
Okay. Fancy.
Well, let's see if I remember how to do it. So okay, and so R is a commutative Noetherian ring, and for prime ideals P, I will write Kp or kappa P is going to be what you think it is. It's going to be the residue field of the local ring, R localized at P, like that. Okay, so let me start by recalling some standard results about homological dimensions. So throughout here, I might as well just say that. So M is going to be an R complex. There are some of the things that I say that are actually interesting. I mean, new and interesting for modules alone. Others are specific to complexes because they remove boundedness conditions in the literature. So M is going to be a complex all the way through. So the first standard result I want to recall is from 1991 of Ramat and Foxby. It says that the flat dimension of a complex is the supremum over integers I, such that so Tor I kappa P M is non-zero for some prime ideal. So of course, in general, so what's the idea? In general, vanishing of the functor Tor on the nose will tell us when we have reached the surpassed the flat dimension. And what they're saying is that to see if a functor is non-vanishing, it's actually enough to just well, enough. There are infinitely many primes. I mean, usually more than countably many, but it's enough to check it at residue fields. And a parallel result that's actually only from 2017 says essentially the same thing, that the injective dimension of M is the largest I, such that Tor I, not Tor, Ext, kappa P M is non-zero. This is joint work with Shrikant. There was something we did years ago. Okay, so now, I mean, these are typical statements in homological algebra. In both cases, to verify the condition, one would have to compute a double infinity of homology modules, right? But okay, it's a characterization. It raises two questions. The most obvious one is the question of rigidity, what is often called rigidity of Ext and Tor. So the idea being, is it possible? Can I find a bound so that if tor I vanishes for all residue fields at some I that's big enough, then I can actually say with confidence that I don't need to check the larger I's. The larger I's will then also just vanish. So that's what's usually known as, well, that's what I call rigidity in this context. So in principle, the idea is to get rid of at least one infinity. And to this, from the paper that I just showed you. So let's see if this works. So we'll keep this one up. So there's a theorem from the paper that I said I would call CIM. So that was joint work with Shrikant Iyengar and Thomas Marley from 2019. So what we proved there was that if for some n large enough, and large enough means that n is greater than or equal to the dimension of the ring plus the homological supremum of the complex. So for such an n, the tor, let's say n plus 1, kappa p is equal to 0. For all p, then the flat dimension is at most n. Like that. So the idea being that, so this is what big enough means. If one moves past the dimension of the ring plus the supremum of the complex, so in the case of a module, just one moves past the dimension of the ring, and just that one tor vanishes for all of them, well, then that's good enough. Then you know that all higher tors will vanish, and that allows you to say that the flat dimension is at most n per the description over here of what the flat dimension is. So that's a rigidity result. And now, how does that come about? Well,
so sorry, Lars, but is the flat dimension of a module not always bounded by its dimension of the ring? No.
Well, if it is finite, yes.
Oh, okay. This is so you want that it's okay. Okay, gotcha.
Yeah. If it is finite, then yes. So it builds on the following. And of course, you could, if you know suffering, of course, that's a different kind of theory. But if you know that the result you said, then of course this is, then of course if it vanishes, is non-vanishing somewhere beyond the dimension, that allows you already to tell that the dimension is finite. But what is actually behind it is, I call this the true rigidity statement is that this statement that you're looking at here is true prime by prime. So if for some prime it vanishes, then tor vanishes, then all higher tors vanishes at that prime. And when you then throw them all together, then you get the statement for flat dimension. So it builds on a result also from the same paper that says that so RMK is going to be local. And so if Ext n plus 1 over R, K comma M is 0 for some n greater than or equal to the supremum of the local cohomology of M, then xi k comma m is 0 for all I greater than n. So that's where it comes from. And the proof of it goes as follows. So the idea is, so first of all, this is a statement about vanishing of cohomology. So I need to turn homology into cohomology. So saying that Tor Kp M0 is, of course, I mean, localization is easy. So this is the exact same thing as saying that locally over the local ring Rp, Kpm localized at P0, and that is by standard matrix duality. That's the same as saying that Ext still over Rp and then MP matrix dual is 0. So what I have to check is just that the vanishing of, so since the vanishing of Tor is the same as the vanishing of Ext, what I have to check is just that the n that I'm looking at here actually exceeds, or is at least the supremum of the local cohomology, is where the local cohomology vanishes, because in that case I can use the Ext result. So notice that n is so what is n? Well, n is, we said, at least the dimension of the ring plus the supremum of the homology of M. Well, that is at least the dimension of the ring localized at P plus the supremum of the complex itself localized at P. Homology might disappear when I localize, but it's certainly not gonna pop up. And this, of course, is the exact same thing actually as the supremum of the cohomology of M localized at P matrix dual. So now I've turned it into something that that looks like the something that has to do with cohomology, and I know that the dimension locally at any local ring, the supremum of the complex plus the dimension of the ring is an upper bound for where local cohomology vanishes. So this here indeed is an upper bound for where the local cohomology vanishes of MP dual there. So this means that the proposition allows me now, because the n is big enough, the proposition allows me to say that all the x's beyond all the x's larger than n will vanish, and that by doing the same argument here, just instead of doing n+1, doing an arbitrary index, that then tells me that the Tors vanish. So that's the proof of that. And then what we did in the paper from 19 was that we said, well, I mean, what can we do? We should be able to do something similar for the injected dimension.
So, Lars, can I ask, so your M is not necessarily Noetherian or finely generated or anything like that, or whatever the equivalent for complexes is?
Which one? The complex, I have no assumptions on the complex.
Okay. Yeah.
I mean, if you look at the statement, it's not interesting unless the homological supremum of the complex. I mean, it's a vacuous statement unless this is a number, right? So in that sense, there's an assumption on it, but there's no boundedness, finiteness assumptions or anything like that. So But here the problem now comes, because the problem we ran into is the following. Well, I don't know if to call it a remark, but one can naively try to do the same thing as we did above and say, well, let's turn this vanishing, or let's turn this Ext with coefficients in kappa p of m. I should be able to express vanishing of that over R. That should be equivalent to vanishing of something locally over Rp. And indeed it is, but the problem is that where in the previous case we just got well, I don't know if the problem, that's just how the world works. When we did it for Tor, we just ended up with with Tor of the localization. In this case, when one does the adjointness in the derived category, one ends up with what is often called the co-localization, or derived co-localization, but it's sort of the only co-localization I care about these days. So one ends up with a statement like this, that vanishing of X with coefficients in Kp globally over R is exactly the same as vanishing locally over Rp, but now not of the localization, but rather the co-localization of the complex. And what is the problem with that? Well, the problem with that is that what can I say about the local cohomology of this co-localization?
Excuse me, Lars.
Yes.
Is this statement in the remark for every P, if and only for every P, or for the same?
Oh, it's true for this, but it's true just P by P. All I'm doing is that,
Okay.
I mean, to derive it, all you do is that you can it's for free to tensor the Kp over Rp with Rp.
Right.
And then you just use adjointness, and so you now start computing the derived term over the local ring, but then you get this strange co-localization.
Right. Thank you.
So what can I say about this thing here? Well, the only thing, what did I do above? Well, I just said, well, I know a way of bounding local cohomology by just using the dimension of the ring and the supremum of the cohomological supremum of the complex. So if I do the same thing in this case, then what do I get? Well, I'll get that this is less than or equal to the dimension of Rp plus the cohomological supremum of this derived completion. And what can I say about that? Well, I mean, in general, not too much. I know that Rp is a flat module, and so an upper bound for projective, I mean, if the ring has finite Krull dimension, then at least an upper bound for the projective dimension of a flat module is still the Krull dimension. So this means that I can say that this is at most the dimension of Rp plus the dimension of R plus the supremum, the cohomological supremum of the complex itself. So, I mean, there's sort of no arguing with that. So that led us in the paper from 19 to state something akin to this. So proposition that if for some n greater than 2 times the dimension of R plus the cohomological supremum of the cohomological supremum of M, one gets vanishing of Ext then the for P, then the injective dimension of M is at most n. So, I mean, of course, one can play around with this a little bit. There are other ways of estimating the projective dimension of a flat module. Here I used the Krull dimension because I already had that invariant in play. If you have control over the cardinality of the ring, you can use the cardinality. But of course, I mean, then it just depends on what you think about the continuum hypothesis. So maybe it's not so interesting. I mean, it's all good and fine. If you know that your ring is countable, you can say that flat modules have projective dimension at most 1. I mean, and that's sometimes useful. But anyway, this is obviously not satisfactory. I mean, this should not be what it is, because we do know that if the projective dimension is finite, then we know that it is at most the dimension of the ring. So it would be, one would expect that it should be enough to look just beyond that. But of course, I mean, if just because the homology, just because the projective dimension is infinite, that does not per se guarantee. There are no holes theorems because there are no boundedness conditions. So just because the injective dimension is not bounded, there's no guarantee that if you pick a random cohomological degree that you'll be able to find non-vanishing X there. There's no such guarantee. So an argument is needed, and well, there is an argument here. It's just that somehow the taking this co-localization instead of the localization fattens the complex a little bit. It means that the complex may grow in cohomology, and to compensate for that, we need to add to the bound. And what I want to talk about today is one of the main results of the main result maybe of the paper that we just put in the archive the other day. What I want to do is that I want to strike this, and then maybe I can call it theorem. So that's the idea. That's what I want to do. So to prepare for that, I need to remind you about cotorsion modules and flat cotorsion modules. So I hope that I can say recall. If not, then this is a crash course in flat cotorsion theory. So an R module C is cotorsion if Ext1 FC is 0 for all flat R modules if. So that's what it means to be cotorsion. Sort of standard dimension shifting will show that actually all higher X's will be non-zero, and actually all higher X against any module of finite flat dimension will be 0. But this is the definition, and that's, I'm not going to need much more than that today. So they're called, so the pair of flat R modules and cotorsion R modules is sort of the original example of a cotorsion pair. Cotorsion pairs get studied in the abstract, but this is sort of the most obvious example. And I mean, of course, the projective and injective modules also belong in a cotorsion pair. It's just that their partner in crime is the whole module category. So we don't need to think of them like that. But there's plenty of evidence that when dealing with flat modules, it is worthwhile remembering that they also have a partner in crime, but that it's not all modules. It's only the cotorsion modules. So Gillespie, Jim Gillespie, shows that whenever you have a cotorsion pair in the category of modules, you can bootstrap that up to a cotorsion pair in the category of complexes. So we get a cotorsion pair with acyclic acyclic semi-flat complexes, or DG flat, or whatever you want to call them, K-flat complexes of flat modules. So acyclic semi-flat complexes and degree-wise cotorsion complexes. That is also a cotorsion pair, now in the category of complexes. Now, what that allows one to do is to do the following. Start with a complex M and take a projective resolution, or semi-projective, we usually call them when it's complexes, but so a semi-projective complex, DG projective complex, that is isomorphic to M in the derived category. So that's a good replacement. But now do something else. Now take that replacement and use the fact that you have a cotorsion pair on the category of complexes. So what Gillespie shows is that just whenever you have a cotorsion pair in the category of modules, you can use them to do approximations. You can always, any module has a surjective map from a module in the left class. So for example, a flat module, and the kernel will be a cotorsion module. Or you can take any module, you can embed it into a cotorsion module, and then the co-kernel will be a flat module. And the same thing, that whole theory just carries over to the category of complexes. So the complex you have here is degree-wise cotorsion, and the complex you have here is, well, the only thing that's it's acyclic and semi-flat. For those who prefer other words, an acyclic semi-flat complex is also, it's a pure acyclic complex of flat modules. Anyway, what this means is that now, because the P was already a complex of projective modules and the A is an acyclic complex of flat modules, that thing in the middle here, which is degree-wise cotorsion, is actually also semi-flat. So this is what is known as a semi-flat cotorsion replacement of M. So the C here is a semi-flat cot replacement of M. So such gadgets exist. And what Peter Thomson has started tinkering with in his thesis and later ended up working out with Tsuma Nakamura is that there's a good notion of minimality for semi-flat cotorsion complexes. Minimality works, as we all know, wonderfully for injective modules or complexes of injective modules. You can always find a minimal semi-flat semi-injective replacement of any complex in the world. For projectives, it famously only works when the ring is very nice, simple or semi-simple or something, perfect or semi-perfect or something like that. And for flats, it turns out for flats, minimality doesn't seem to work very well, but for semi-flat cotorsion complexes, there's actually there's a good notion of minimality. So that's Nakamura and Thomson. So every complex over a ring of, I mean, it's actually true in general, but I'll use the result finite Krull dimension has a minimal semi-flat cotortion. Now, minimal here means that every homotopy equivalence from the complex to itself as an isomorphism. That's the usual notion of minimality in homological algebra. So that's what it means. Now, this might not be so interesting if it wasn't for the fact that they can describe the structure of them. And I didn't tell you about the proposition that I said everything was hinging on over here. The one here about vanishing of Ext, rigidity of Ext. That result depends crucially on the existence of minimal semi-injective replacements. And so our hopes started rising when we got something similar on the flat side. So there's a structure. So each module Fi is just a product. I'm going to call it F, semi-flat replacement F. So it is a product over all primes of a free module so these index sets are sometimes called the dual Bass numbers. They occur in some of Enoch's work and certainly in his student Schuss book on flat covers. They occur there. So they're just index sets, and then you have to complete this whole thing here over RP. Oops. So that's what they look like. And the beauty of that is that if you remember how injective resolutions work, when you have a minimal injective resolution, you know that it's built out of injective envelopes of quotients by prime ideals, and we understand exactly what happens when we take torsion. That throws away the things that sit below, and when we localize, we throw away the things that sit above, right? I mean, localize a minimal injective resolution at some prime. What you're doing is you just go in degree by degree and throw out E of R mod Q for Q's that are bigger than the prime that you took. And taking torsion just does the opposite thing. And the whole key to what's going on here is that for a minimal semi-flat cotorsion, the completion functor and the co-localization do the exact same thing. So this means that this gives us control over what this it gives us a way to compute. Remember, it was this pesky co-localization, derived co-localization, that pushed the bound up in the paper from 19. That's because we didn't have any control over what that co-localization looked at. And what will happen now is that resolving the complex appropriately, losing one of these minimal semi-flat cotorsion resolutions or replacements, we'll be able to control exactly what the things look like and get the right bound. So, and as I said, I mean, this is flat cotorsion theory has been around for a long time. There are applications of it in a certain sense in commutative algebra, but not something that has sort of hit so close to the core of questions that many people are interested in. So let's see. So we can now prove the theorem. So let me just write proof in red because it's the proof of the red theorem that I'm starting now. So so we take a minimal. So F is going to be a minimal semi-flat cotorsion replacement of M. Okay, and because the as Mi is I can assume that Mi is 0. On one side, which side is it that I want? Yeah, I can set S. Well, let's set S to be the supreme one. So I set S to be the cohomological supremum of M. I mean, I'm trying to bound injective dimensions, so the thing is ultimately going to have a finite cohomological supremum. I cannot say that F stops at S, but I can say that it stops in high degrees. It will not necessarily be. It will not in general stop right at S, but it will extend for at most the dimension of the ring past it. So, and actually, what's even better, one can say what it looks like, because F is going to look like this. Then there's F in degree S, and that thing is going to be a product over just all p's in spec of, just as before, localizations of Rp, some index set B localized. Now, what happens is that, well, we can do one more. So when we go to S plus 1, that thing is no longer a product over everything. Now it's only a product over the primes where the dimension is at least 1. And it just continues like this, and you end up in degree S plus the dimension of R. And there, all you have is a product over P's where the dimension of R mod P is the dimension of R. So that's what it looks like. So they have a description of the tail. So the complex, the homology or the cohomology of the complex ends. Oops, that's not what I wanted. I just wanted this one. Ends here at S. Normally, you would think that you could choose your resolution. If I was just choosing a projective resolution, I would be able to choose the projective resolution starting here and just working out to the left. They can't quite do that. It's because the way they construct it is a totalization of a double complex, and that totalization sort of spills over a little bit on the right-hand side. But they have complete control over the tail. So out here, of course, there's no cohomology. This whole thing out here is exact, and they can say what they look like. So now, what is it that I want to compute? Well, so it is actually enough to prove it is enough to prove that the N is at least the supremum of the local cohomology, because then I can apply the same proposition from the paper from 19, the one that talks about rigidity of Ext. I can use that as long as I can prove that the N, my N, is greater than or equal to the extent of the local the P comes up here, the local cohomology of the co-localization. That is enough. So this means that the complex I need to look at is the right-derived torsion functor of applied to the co-localization. Now, there's a trick from back in the day when it was worked out firmly that derived torsion and derived completion are adjoint functors, and it comes in handy here. So it says that it generally, I always think of it as saying that if you did both complete and do torsion, then it's actually only the last thing that you do that survives. So I can throw in the derived completion at the maximal ideal, PRP, and then take cohomology, and then take torsion. No, it doesn't change anything. But now by, well, it's not independence of base, it's almost the opposite. But one can prove that when you localize, when you complete an R-harm like we're doing here locally over a local ring RP, or it works for any change of rings, you could actually just complete the thing that you are with respect to P at M. So the completion locally at the maximal ideal of RP of this RP complex is the same as the co-localization of this thing where I've here completed over R at P. Those two things are the same. So now the next question is, how do I compute any of these things? Well, I have my semi-flat cotorsion replacement. So I can replace F by that. And then I can apply the right derived completion can be computed also using semi-flat replacements. It doesn't have to be semi-projective, is the usual thing that flatness works. So I can just complete this one at P. It's all that happens when I complete at P is that I go into the minimal semi-flat cotorsion replacement, and then I'm just throwing out the primes or the completions of free modules at primes that do not contain P. So I'm just throwing out everything that's below. And it's still a bounded on the right complex of flat modules. So this is still a semi-flat replacement. There's no problem with that. So this means that to compute the derived harm, I actually only need to, I can just use this thing because R localized at P is a flat module. Normally to compute R harm, I would have to derive this thing here. I would either have to derive this one, I don't want to do that. So that one I would have to derive injectively. But since this one is flat, I can actually derive it with anything that's Ext orthogonal on flat things. And that's what flat cotorsion things are. So this means that this complex here computes the derived harm. But now I know what this complex looks like. Because if you go back to here, I know what the tail of this complex looks like. So this means that I can now say that I can now say that the supremum of the local cohomology locally at PP of R harm over R localized at P comma M. Well, that is the supremum of homology of just the harm. Well, I can say that it's, I should do it like this. What I can say is that this is less than or equal the dimension of R localized at P plus just the cohomological supremum of, this is just the usual of the co-localization. This is just usual estimating the bounds on local cohomology by saying it can't go beyond the dimension. And now I know what the complex that I'm estimating the cohomology looks like, because this is just the cohomological supremum of harm over R RP of course this M here should in both cases be lambda of M. And so this thing here is just lambda P applied to F. And now if we look at what it looks like, of course, when I'm throwing away, when I first I complete, that means I throw away primes that sit above P, And then when I co-localize, I'm now throwing away primes that sit below. So in other words, I am over here, I'm just picking out the components that correspond to this particular prime P. Those are the only ones that survive doing these two consecutive operations on the semi-flat cotorsion replacement. So this means that it stops. I mean, there's simply no room. There are no such P will never. P doesn't satisfy this condition, so it simply stops at the dimension of R mod P. So this means that this here is at most the dimension of R mod P plus, well, plus S, and then how much more than S? Well, the dimension of R mod P. And now the dimension of R mod P plus the dimension of R localized at P is together at most the dimension of R plus S. And this was less than or equal to N in the statement of my theorem. Right. N is greater than or equal to the dimension. N is greater than or equal to the dimension of the ring plus the homological supremum of the complex. So there you see how it's simply the structure of the semi-flat cotorsion replacement that allows us to estimate to give us a better estimate on what the cohomological extent of the co-localization is, and that way we get the bound. And I mean, of course, part of me wants to say that this bound is sharp. Morally speaking, it is sharp. But as a logical statement, if you want, just think of modules. So this is just a quirkiness, but maybe it's worth saying. If you look at local cohomology, is just a co-limit of X, right? Of powers, R mod powers of the maximal ideal and M. So these guys here are actually they're all finite length. So there's no way this X can vanish unless XKM vanishes in the first place. So this means that technically speaking, you can subtract 1 from the bound here if you want. And it still remains valid. The only point is just that you can subtract 1 because it's actually not the assumption will never be satisfied. And when you say it like that, then this bound is optimal. You can't do better. So yeah, that was what I wanted to tell you about.
Thank you.
Thank you, Lars. Any question for Lars? Or Hans?
I was thinking now, for just naively looking at the bound that you got on the last, or the third dimension RP plus S plus dimension of R mod P. Mm-hmm. So it seems like the first one is bounded by dimension of R, and the third one is also bounded by dimension of R, and that's why you have 2 times the dimension of R. Yeah,
in a certain sense, yeah.
But it's not as simple as that. You cannot say that the bound of these, whatever you call this co-multiplication, is just given by that sum.
I mean, you can, in the sense that the proof is here. But I mean, it was not I don't know any. I mean, I don't know a proof that would give a bound. I don't know any other proof that would allow you to give a lower bound on the vanishing on the cohomological extent of the co-localization. So I mean, yes, in a certain sense there's a lemma here that might be worth stating in its own right, namely that the cohomological supremum of the co-localization is I mean, if you just take the co-localization of a module, how much can it grow? Well, it can't grow by the full. It's not going to grow by the full dimension of R. It's actually at most going to grow by the dimension of R mod P.